for section 3.1, you can see that I have the slope formula written on the paper here. The only thing I did different here, you notice that instead of using A, I used X. Okay. Keeping in mind though that A values are essentially X values here. It really doesn't matter which variable we use. Okay, I'm writing it in this form because we're going to put a name on this particular formula now. Okay, and the name of it is called the derivative. Okay, so what we've been finding here by doing that process is we've been finding the derivatives for some functions. Okay, so from here on out, anytime we do that, anytime we find the slope of a function at a general point, okay, we're going to call that the derivative. Fair enough? All right. So if we look at a simple function like x squared, f of x equals x squared, if we were to go ahead and plug in the x plus h and the x and so on and calculate it and find the limit as x or h approaches 0, we would find the answer to be 2x. Okay, we've done that a few times now, or we've done that with x squared. Okay. All right. Now, what I want to talk about here first is the graph from a graphical standpoint. Okay, why this works. We've talked about this a little bit already, but when I look at the graph of y equals x squared, and I also graph the derivative on the same coordinate plane, okay, keep in mind that what we should notice here is that the y values of the derivative, okay, match the slopes of the function. Okay, so for instance, if we are on this left branch over here, okay, the slope of the curve over here, if I were to find the derivative, if you will, at any of those points, okay, my answer should be negative on that left branch. True? Okay, and what do you notice about the y values of the y equals 2x, or f prime equals 2x? Okay, they're all what? They're all negative as well. Okay, and another thing to consider too is that at 0, at the vertex of this parabola, okay, we said that the slope was 0. Okay, notice the y value of the derivative is also 0. And anything to the right, where the y values, or where the slope values are positive, okay, the y values of the derivative are also positive. Okay, and not only are they positive, but as I go to the right, okay, what's going on with the slope of x squared as I go to the right? The slopes are getting what? And is the slope here the same as the slope here? No, it's getting bigger. Okay, the slopes are getting bigger as we go to the right. Well, what's happening with the y values of our 2x function as we go to the right? They're getting what? They're getting bigger. Okay, same thing going off left. As I go to the left, the slopes are getting, okay, more negative, if you will. Okay, bigger negative numbers, and then this one is getting bigger also, okay, in the other direction. Okay, so one thing that to note is that if we do find a derivative of a function, okay, its y values should match with the slopes of the original function. Just for argument's sake, for this particular problem, if we look at x equals negative 3, okay, at x equals negative 3, if we put a negative 3 into our derivative, okay, which indicates the slope of our curve at any point, okay, we should get an answer of negative 6. So if I went over here to negative 3, okay, just say it's there for argument's sake, and I calculated that slope, either by picking 2 points that were very close to each other at that point, like I did with the calculator, okay, we would find that, okay, the answer is going to be negative 6. Okay, we can verify that with the calculator, okay, with our tables, etc. But bottom line is the y values of the derivative are always going to match up with the slopes of the function. Okay. All right. Now, I want to talk about notation over here on the left-hand side of this paper. Okay. I used the notation up here with a little apostrophe. Okay, we call this prime notation. Okay, when I write the derivative, okay, instead of writing the word derivative, of course, and mathematicians always use symbols instead of words because I don't like to write very much, right? Okay, as little as possible. So instead we use the symbol f prime. So if our function is given as f of x, then when we list the derivative, we say f prime of x, and that's the way we say it, f prime of x is equal to 2x. Okay. We also, in y notation, if we say y equals x squared, okay, then we would list it as y prime, and that also represents the derivative. Okay. And then there's another notation that we call Leibniz notation that we'll be using quite a bit throughout the class, but it's dy dx is how we say that. Okay, we don't say dy over dx, we just say dy dx. Okay, so when you read that, you're going to read it to yourself as dy dx. Okay, and all this represents is the derivative of y, okay, whatever the dependent variable is. Okay, because if we weren't using y and x, if we were using p and n or something, okay, it would be dp dn. So ultimately, it's dy, which is again the derivative of y, okay, whatever the dependent variable is with respect to x. In this case, that's the independent variable. Okay, so if the independent variable is x and the dependent variable is y, then the derivative is listed as dy dx. Like I said, if we had something like a equals pi r squared, with those two variables instead, then in Leibniz notation we would list that as dA dr, okay, the derivative of a with respect to r. Okay, keeping in mind that, again, the top is the dependent variable, the bottom is the independent variable. Questions so far? Alright, one other piece of notation, also it's a version of Leibniz notation. If the function is given to us as f of x, we can also write, and we'll see this quite often too, is that we'll see d dx of f of x. No, so I've said that in words. I said it as d dx, okay, not d over dx. So if we write d dx of f of x, that also means, okay, we need the derivative. So in the instructions for your homework, it's going to say, given f of x, find d dx. Okay, and you'll need to understand that that means find the derivative. Okay, and once we know the directions and understand the notation, okay, then it's just a matter of applying the limit definition that we've been using. Okay. Questions so far? All right, I want to visit the graph part more closely. Okay, and I have on here, I've already given you the answer here, but I want to see why it's the answer. If you look at the sine function here, okay, I want to explore the relationship between the function and the derivative in terms of the graph. Okay, if we look at the sine function, which I have in bold curve here, and I have the cosine in dashed curve, if you will. Okay, I want you to think about the fact that I have here that y equals sine x, then y prime is equal to cosine x. Okay, which is a new fact for us today that we didn't know before. Okay, that cosine is the derivative of sine. Okay, and I want you to think about y graphically. As I go from 0 to pi over 2 with the sine function, okay, what are my slopes like? They're positive. Okay, the slopes are positive. Okay, so we should expect that the derivative's y values be what? Positive. Remember, the slopes of the curve and the y values of the derivative need to be what? Need to be the same. Okay? Because again, the derivative tells us what the slopes are like. So whatever the y values of this are like, okay, is going to tell us what the slopes are like for the function. Okay? Now, you'll notice also that as I get closer to pi over 2, okay, what's the derivative going to be at the top of this? It's going to be 0. And notice, what does my cosine do as I approach pi over 2? It's close to what? It's close to 0. In fact, at pi over 2, it is 0, isn't it? Okay? So again, the y value of the cosine is 0. And the slope of the sine is what? 0. And again, because the slope of the function has to be the same as the y value of the derivative. Okay? And you'll notice that going from pi over 2 to pi, what are my slopes like? Slopes are negative. True? So if my slopes are negative, then what should I expect from the y values of the derivative? The y values are also what? Negative. As I go from pi to 3 pi over 2, okay, what are my slopes still like? Okay, they're still negative, aren't they? And notice, what about the y values of the dotted curve? The y values of the dotted curve are still what? Still negative. And then finally, as we go from 3 pi over 2 to 2 pi, okay, what are my slopes back to? Slopes are back to positive. And if you look at the y values of the derivative, the y values are what? Positive. Notice again, what's the slope at this point at 3 pi over 2? the slope is 0, what's the y value of the derivative? 0. Okay, again, the slopes of the function have to match up with the y values of the derivative. Questions so far? Okay, one thing we have to be careful about is going back to this branch from 3 pi over 2 to 2 pi. Okay. Does the fact that the curve is below the x-axis have anything at all to do with its slopes? We might say, wait a minute, it's negative there. No, it's not negative, okay, because we don't care about what the function values of the function are. We care about the slopes of the function. Okay. So since the slopes of the function are positive, we should expect that the y values of the derivative are also positive. Fair enough? Eli?
How is the slope of cosine positive in the first?
The slope of the sine is positive. Therefore, the y values of the cosine are positive. Okay. Remember, the sine is the function, okay, and the cosine is the derivative. Fair enough? Okay. Questions so far? All right. Let's ask this question then. What about cosine? What if I told you that the function was cosine? Okay. Can we automatically assume that the derivative is sine? Maybe. Let's find out. Just based on what we know from graphs. Okay, we know that key point-wise, our cosine function, I'll do that one in bold this time. Okay, so there's our cosine function. All right, and if you look at the cosine function, what do we see right off the bat? Well, let's start right here, because we know, and I'm just going to extend this into the negative territory a little bit. Okay, first of all, what do we know about what would be the derivative of the cosine at 0? It'd be 0. So shouldn't the value of our derivative be 0 then? So I'm going to plot that point. Okay. Now, right off the bat, we might say, well, pretty good chance that it might be sine then, because that's where sine starts, right? At 0, 0. Okay, but what do we notice about the derivative as we go from here to here? Okay, yeah, the derivative should be negative, shouldn't it? Okay. Matter of fact, it should be negative all the way till we get to pi. Okay. So if we do that, I'm thinking about also, and before I draw in the other part, what do we know about the derivative at this point, at pi? The derivative here should be 0, so shouldn't we have another point if we're plotting points to make our derivative here? Okay. And then also knowing that this goes here, where should we be back to? We should be back to here then at 0 again, shouldn't we? So we got to keep in mind I'm plotting key points to develop what the picture of the derivative would look like. And once we have the picture, maybe we can predict what the actual answer is algebraically. Okay. So let's talk again about, we said that between 0 and pi, the derivative of cosine is negative, because it's going down, it's decreasing, if you will, right? Okay. And so therefore, from here to here, I should have negative y values. Now I want you to think about too, if I were to draw this perfectly, okay, when I get halfway between 0 and pi, which is pi over 2, okay, shouldn't the derivative be as steep as it gets, if you will? Okay, shouldn't the slope be as steep as it gets? Because we know it's 0 here and it's 0 here. It goes negative for a time, but then it goes back to 0. So it goes negative, it gets more negative, and then it gets less negative back to 0 then. True? So wouldn't that be the same for the y values? Wouldn't I get negative, gets to some value, and then get back to 0 again? So wouldn't it make sense that that would be a picture of the curve in this situation? Okay. And knowing what we know about sine and cosine too, and the values at the points where we cross the x-axis, okay, would it be terribly surprising to you if the answer here was -1 for that maximum slope, if you will, or minimum slope if you want to think about it as positive, negative? Okay. And then also from pi to 2 pi, what's going on with my slopes? The slopes are what? They're positive, and again, they start at 0, they get bigger, and then they go back to 0. So is it surprising that the picture might look something like that, and have that also be up to 1? Okay. Right. So again, the key issue is that the slopes of the function, okay, have to match up with the y coordinates of the derivative. So at this point, we should be able to make a prediction. Y prime would be then what? That's negative sine x. And it is. So those are two important facts that we're going to work with. The algebra of that, okay, is something that we aren't going to worry about for the time being. Okay, so we'll revisit that later. But like I said, these are good to use for understanding the relationship between function and derivative from a graphical standpoint. Okay, so like I said, the algebra of why that's true. Okay, because really the only algebra we know at this point is using the limit definition. So we'd have to put, for sine x, we'd have to put sine of a plus h minus sine of a over h and do some algebra there. Okay, and like I said, we'll visit that later on. Okay, right now I just wanted to see the graphical part of it. Okay, questions so far?